All right, guys, so we worked really hard, actually, in the last video to dredge through the details of finding a formula to take the derivative of a function, which is a quotient to functions. And almost ceremoniously here, let me erase that work. Not to say that that work was not worth it, because it totally was, but the value of that work is now never having to go through that process again. So the fact that we've gone through the details of that work, we now have ourselves a formula that simply needs to be applied. So how could you apply such a formula? Well, let's go through an example to see it in action. So if you had a function that was, let's say, square root x over x squared, find the derivative of that function. Here's a perfectly valid function. You could plug in a value for x and get something back in return. Plug in x equals 4, you'd get out 2 over 16. Plug in x equals 9, you'd get 3 over 81. Plug in x equals whatever, you'll get out whatever the square root of x is divided by whatever x squared is. I mean, technically you'd have to plug in x's that are positive or 0 because negative numbers don't have square roots among their real numbers, but the long story short is this is a perfectly valid function. This function, if you started looking at its inputs and output pairs, would have a graph. That graph, zoom in on any point, would have a tangent line, and the tangent line at each of those points would have a particular slope. What is the slope of those tangent lines? Well, that is the derivative. And now, while you may not be able to visualize what this function looks like, because this is probably a pretty crazy function to look at, I claim that we actually have the ability to develop a formula which tells us the slope of the tangent lines. And the formula for that is that, albeit cumbersome, formula that we cooked up in the last video, spending, what, 11.5 minutes doing. The long story short is you can compute the derivative of any function, which is a product of two functions, using this formula. So note, the function that we are encountered with here is itself a product of two functions. It is of the form f of x over g of x. And what is the derivative of a function that is itself a quotient of two functions? Well, you carbon copy the second guy, or the guy that's downstairs, you multiply by the derivative of what's upstairs, you subtract a carbon copy of what's upstairs times the derivative of what's downstairs over what's downstairs squared. Now, again, this is a mouthful. It took 11 minutes of detail to figure it out, but here's the beauty of it. We can take this expression, put this formula to work, and come up with a subsequent expression for the slope of the tangent lines to this function everywhere. So what is g of x? G of x is just simply what is downstairs, that's x squared. What is f prime? That is 1 over 2 square root x. Well, we had computed that previously, minus carbon copy of what's upstairs, that's square root x, times g prime. G prime is the derivative of what's downstairs, that is 2x, over what's downstairs squared, so that would be x squared. Squared, well, hell, x squared times itself. You know that x squared squared is just x squared times x squared, which is a total of 2x's times 2 more x's, which is x to the fourth. So let's just write it for what it is, x to the fourth, and we're done. We've got an expression now for the slope of the tangent line to this function. We've got an expression for the derivative of this function. The technical details here were not many. We really just had to follow the formula. The formula had a bunch of technical details, but look what we've done here. We've taken the derivative of this function, and it is cumbersome, but it's done. And that's pretty cool.